Good morning, students. In the last class, we have concluded our discussion on spins. Now, let us move on to the transient heat conduction. I told you in Unit 2, we have completed till the sixth one now. That is, till here we have completed. Now, the seventh one is left out. The seventh one, what you have is transient heat conduction. Okay. So, in today's class, let us start this transient heat conduction. Transient heat conduction. This is also called as unsteady heat conduction. Transient means unsteady. Okay, that is here temperature is varying with time. Temperature is varying with time. For that matter, any given property in general, if it is varying with time, then we call it as unsteady state or transient state. Okay. In this transient state, we'll be looking at in this transient state, we'll be looking at three different cases. The first one is lumped parameter system. In lumped parameter system, we will consider certain properties for a given material that I'll tell you while discussing that. And the second one is semi-infinite solid. The third one is infinite solid. Okay. Now let us start our discussion on the lumped parameter system itself. Okay. The first one will start lumped, L-U-M-P, lumped parameter. See, in this lumped parameter system, what we will do is, see, so far what we have done is, we have considered that the temperature will vary with respect to the position. Temperature, if it is a function of x comma y comma z, then we say that temperature is varying with respect to position. Varying with respect to position. If the temperature is a function of time, then we say temperature is varying with respect to time. If you consider both t of x comma y comma t, sorry, x comma y comma z comma t. If the temperature is a function of all these parameters, then what we say is temperature is varying with respect to both position and time. Okay. In most of the practical cases, what happens is it will vary with both position and time. Okay. But for the sake of simplicity, we will consider each case. Okay. In the discussion so far, what we have done is we have considered the temperature is varying only with respect to the one direction. Now, what we will do is we will take the temperature with respect to the time alone. Okay. That is, what is the meaning of this? Meaning of this is temperature is not varying with respect to position. So, in lumped parameter system, what happens is temperature is not going to vary with respect to the position. Okay, wherever you take in a given body. Okay, let me draw a body here. draw a body here. There's something like this. This is the body here, and it's something like this. Now, in this body, the temperature, if you measure, it is going to be same everywhere. You measure on the top, you measure the temperature on the top, on the bottom, on the corner, on the side. Everywhere, the temperature is same. Okay, T is equal to, let us say, 20 degrees centigrade. So everywhere it is 20 degrees centigrade only. It is not going to be a different value or a lesser value or a greater value, something like that. Okay, everywhere the temperature is being maintained constant. Here, everywhere. Okay, we put the point here. Any point at any point in space of the system, temperature is same. Okay, that you call it as a lumped parameter system. Okay, if you have to call something as a lumped parameter system, it has to satisfy at least three conditions. Okay, lumped parameter system has to satisfy at least three conditions, and first among them is uniform temperature throughout. Uniform temperature throughout the body, like I have shown here. Okay, everywhere at any given position, the temperature is remaining the same. It is not going to vary with respect to the position. Okay, that's what the meaning of uniform temperature throughout the body. The other way of saying it is temperature gradient. Temperature gradient is 0. What is temperature gradient? It is dt by dx. In your Fourier's law of heat conduction, dt by dx you will have, and this dt by dx is 0. Temperature gradient is not there. Okay, that is one thing. And how these things can be obtained? Okay, you are saying that the temperature will be uniform throughout and the temperature gradient is 0. When will this happen? When this can be a reality? That's the question. Okay, it will be a reality only when you have a material of high thermal conductivity. High thermal conductivity. Okay, let us say I take a huge water body. It is filled with water. Okay, you have a huge water body here, and this huge water body, what you have done is you have kept some body here. Okay, something like this. There is a body here, and this body, let me say that initially this water is at 20 degrees centigrade, and my particular body that I have dropped is at 100 degrees centigrade initially while I am dropping it. Okay, when I am dropping it at 100 degrees centigrade, if it is having, let us say it is copper of high thermal conductivity of material. So when I drop it here, immediately heat will transfer from high temperature body to the low temperature body. This is the direction of heat transfer. But while transferring the heat at any instant of time, at any given instant of time, comma, the temperature is same throughout the body. The temperature is same throughout the body. That's why this can be said like the temperature is varying only with respect to time. With respect to position, it is not going to vary because this is small enough to have the same temperature throughout. At the same time, it is having high thermal conductivity. Since it is having high thermal conductivity, the same heat is going to come out or go in. If the reverse is happening, the heat is going to go in. Okay, but in this case, heat is going to come out. Okay. So like that, the lump can be considered, and more appropriate way of quantifying this will require something called as Biot number. I must tell you what is Biot number. See, Biot number is a dimensionless number, and if I have to express it in a known terms, it is like this: HL by K. Okay, H is your heat transfer coefficient. Heat transfer coefficient measured in watt per meter square Kelvin, and K is the thermal conductivity, which is measured in watt per meter Kelvin, and LC is some dimension. Okay, it is called as characteristic dimension. So what is this characteristic dimension? I will tell you, and it is measured in meters. Now tell me, what is the unit of this? This will not have any unit, because see, in the top you have watt per meter square Kelvin in place of it, and into M you have by, in the denominator you have watt per meter Kelvin. This M goes, this whole watt per meter Kelvin goes, so no unit. That's the thing here. Next thing is, if I have to define it properly, how I have to define it. Okay, see, on the top you have convection. Okay, convection heat transfer. On the bottom, what you have, K by L. K by L, you will actually have in Q is equal to K by L into A into dt, or I can write it like T minus T. This is Q conduction. If I write Q convection, it is H into A into T minus T. So this T minus T goes, if I divide it, this A goes, and what remains for you is HL by K, and I'm calling this as Biot. So on the numerator side, what you have is convection heat transfer. On the denominator side, you have conduction heat transfer. Okay. So where is conduction happening? Conduction will happen inside the body. This is your body, and inside this body, this conduction will happen. Okay. And where is the convection happening? This convection will happen with respect to the fluid. There is a fluid around here, and in this fluid, this convection will happen. Okay. So that's what about Biot number is. And if you have to say whether a given system is lump or not, is decided by Biot number. Is if the Biot number, if it is less than 0.1, that will be a lump. Okay. If Biot number is not less than 0.1, that is greater than 0.1, that will imply it is not a lump, meaning the temperature is not varying with respect to time alone. Okay, it is going to have some other thing also. So this is very important thing as far as your lumped parameter system is considered. Okay, in a given problem, what you have to do is you will actually have to check with this Biot number. If you check the Biot number, this Biot number should fall below 0.1. If it is falling below 0.1 only, you have to apply the methodology that you are going to use here in this case. Okay. Now, okay, let me go to the mathematical part of this particular problem. Okay, like I have taken previously. Now also I am taking. This is my water body, or the H, whatever that is giving H. and then I will have my lump here. It need not have a definite shape. It can have any given shape. We call it lump. And then now what I will do is I will take energy conservation. If I have to take the energy conservation, what it will be like, heat transfer out of body is equal to heat transfer to ambient. If I have to get heat transfer out of body, it is heat transfer by conduction with generation also, and that will be equal to mCp dt. Okay, you know this. What is the heat transfer to ambient? It is HA delta, heat transfer by conduction. Okay, this is how you will get. Okay, see here the temperature is majorly varying with respect to the solid itself. So you can write dt here. But on the other side, it is going to be like T minus T infinity you can have. Because T infinity is a constant value, you can write it like T minus T infinity on the other side. See, to balance the unit, here on this side, you have watts. On this side, you have joules. Okay, you take the each parameter here kg per mass, joule per kg Kelvin here, and Kelvin here. So what you have is joule basically here. So this joule need to be converted into watt. So what you have to do, 1 by second you have to do. So for that purpose, what I will do is I will write this mCp dt by T, because temperature is going to vary with respect to time. In my case, okay, that I have considered here for the lump. So I'm considering the change of temperature with respect to time only. So then H into A into T minus T infinity. You see, when I say this A, this is the area of convection. I'm representing AS here so that it will represent the surface area of a given body, whole surface area of the given body. T minus T infinity somewhere. Now what I will do is, I will do variable separable. I have a temperature T here, temperature T here on both sides of my equation. I will get this T minus T infinity onto my left hand side. For that, what I get is 1 by T minus T infinity into dt is equal to H into AS by M into Cp into dt. That is your mathematical expression. Anyways, so now what I have to do is I have to integrate it now. Now that I have done variable separable, once I'm done with the variable separable, I have to integrate it. When I integrate it, it is like 1 by so this is the expression. There seems to be some problem. Okay. 1 by T minus T infinity into dt is equal to integral on the other side also I will take. See, when I'm taking this integral on the other side, this HA by MCP, all this is constant. So I can keep it aside into integral dt I can take. Now, see, one important thing I have missed is this dt by dt can be negative. Okay. So what I'm putting is I'm putting this minus here, this minus here. I'll take this minus onto the other side over here. So integral 1 by x dx is log x. So what I'm doing is I'm going to take this as log, that is ln. I will take to the base e, log to the base e. I'm taking ln of t minus t infinity. I will take here, and then on the other side, I will take minus h into a by mcp. I'll keep it aside. And integral dt is t. This is simply t. Now, what I want to do is I want to get I want to integrate it over certain limits. Okay. So if you have the limits only, this solution you will have. Otherwise, you cannot have solution, because this is a problem wherein only time is varying. You cannot have boundary conditions here. You will have something called as initial condition and final condition. Initial condition and final conditions we have to use while solving this problem. That is, at time is equal to 0, what is the temperature value you have to take? Let me call this temperature as T naught. T at 0 is time. That's the meaning of it. Then time, let me say so and so time T. At this time, the temperature is equal to T x, let me say T x, or T with respect to T itself. Okay, simply it is written as T itself. Okay. You will understand that when we solve it. Anyways, so now when I take this, I have to apply the appropriate limits here. When I apply the limits here it is going to vary from T naught to T T, and this is going to vary from 0th time to T time. Now I have to put the appropriate limits here. Now, if I substitute the limits, what I get on my left hand side is t minus t infinity by t naught minus t infinity. Okay, this is what I got on my left hand side. See, when I say t, at time t. Okay. You can put it like this also. In some textbooks, people write it like this, t of t also people write. And I think it's okay. Is equal to minus HA by MCP into the T minus 0. Okay. Simply you will have T. So what I get here is ln of T of T minus T infinity by T naught minus T infinity is equal to minus of HA by MCP into T. So this is the expression that you've got, but there is a simple way of expressing this particular expression. For that, what we'll do is we will introduce M is equal to density into volume. That is, we know that density is equal to M by V. So what we will write is M is equal to rho V, we will write. So this expression will turn out to be minus HA by rho V into Cp into T. Right? So this is how is it, your expression is like now. T of T minus T infinity by T naught minus T. This is your expression. Okay, this you can call it as a final expression, and you can use this for calculating various temperatures at different times. Okay, if it's so and so time, what is the temperature? You can use this formula and find it out. But there is even simple way of expressing this particular one. Okay. How to express that? Okay. For that, we must know what is called as. Let me put this as an expression. keep that expression aside and let me define what is Fourier number to you. See, Fourier number is a number basically which will is a dimensionless number which will have time in it, and it is represented with FO that is equal to alpha T by LC square. Fourier number is written like this: alpha T by LC square, where alpha is thermal diffusivity, and it is measured in meters square per second. And T is time measured in seconds, and LC is characteristic dimension, and this characteristic dimension is measured in meters. If I have to take it in the units terms, on the top you have meter square per second into second by meter square. Second cancel. This second cancels out. Meter square cancels out. Will not have any. So that's what alpha T by LC square is. Now what I want to do is I want to express this whole right hand side in terms of the Fourier and Biot. What I have is minus HAS by rho V into Cp into time. This is what I have. Now what I want to do is I want to express this in terms of Fourier. For Fourier, you need alpha. Alpha is not there in this particular expression. How do I get alpha? What is alpha formula? Alpha formula is K by rho Cp. Okay, I have rho Cp in the denominator. So what I'll do is I will multiply this with K and divide it with K. Okay, so K by K I will take. So K by rho Cp I will put aside into H into AS by K into V into T. I will put this aside. Okay. Now K by rho Cp is there now. In this place, alpha I can write alpha into HAS by KV into T. Now alpha T is obtained. That is the numerator of my Fourier number is obtained. Okay. Let me put it aside. HAS by, see here, what I'll do is I'll write H by K into V volume by AS. Okay. See what is characteristic dimension means? Characteristic dimension means LC that is equal to this volume by area. Okay, that's why I have written the volume by area here so that I can represent that H by K into LC. See, what I need here is LC square. So I'll divide it with LC square here and H by K into LC I will write. To compensate for this LC square, I am writing the LC square in the numerator also. Okay, this LC and this square goes, and what I have here is this particular term is nothing but your Fourier number. And if you look at the other number, H by K, HLC by K. So what I got is essentially Fourier into Biot. Okay, so simply put, the whole expression that I have on my right hand side, this side, I can write it like minus of Biot into Fourier. Okay, this minus we will have anyway. So what I got is ultimately this ln of T minus T infinity by T naught minus T infinity is equal to minus Biot into Fourier. Okay, that is as simple as that. Yeah, and it can also be written like T of T minus T infinity by T naught minus T infinity will give you e power minus of Biot into Fourier. This is one important expression that you must remember. Of course, this will also be in database. But it's good to remember this particular expression also. This is the easier way of the previous one. Simply, if you remember the Biot number formula and Fourier number formula, this is simply e power minus of Biot into Fourier. That's how you will do. Now, if in a given problem, if he is asking you to solve the given problem, first what you have to do is, if it is by lump, you have to check the Biot number, whether it is less than 0.1 or not. That is the first thing that you should do, and then move to the other discussion. Okay. So that will also help you in substituting the Biot number here directly. That's the point I want to convey. And one another thing is the characteristic dimension. The characteristic dimension, I already told you, characteristic dimension. It is called as characteristic length when you are measuring length. Okay, that is LC is equal to V by A, volume by AS, or simply A also you can put. Right. If you are taking it for a sphere, let us not go for a sphere, let us go for a cube initially. If you are going for a cube, the what is the value of this characteristic dimension of it will be like the volume is, if the side is A, the volume is A cube. What is the surface area of the cube? It is A square on 6 sides. So simply put, for cube, for cube, the LC value is equal to 1 by 6. That's the point there. Okay. The other thing is for cylinder. For cylinder, what is the LC value? If you write it is again volume. For cylinder, the volume is 2 pi uh, r square into L. That is your volume. And if I have to take the surface area, it is pi r square of the sides, and on the others 2 pi r L. Okay, this is another area. So if you take out the pi and r appropriately, everything will get cancelled. Those things will get cancelled, and what you have in the final thing is r into L, sorry, by 2 into r plus L. So that is the thing. Yeah, that is your cylinder characteristic dimension formula. Then move to sphere. So the sphere, the LC value. The volume of the sphere is 4 pi 3 pi r cube by the area of the sphere. It is 4 pi r square. So what you have is simply r by 3. Not simply 1 by 6, it is a by 6. Yes. This square and cube goes a you will have. For cube, change it, it is not 1 by 6, it is a by 6. All right. Like this for anything you can write. Okay. For any given case, you can write it. Only thing is you should know the formula for volume and the area. You can find out the characteristic length appropriately and put it in Biot, which is HLC by K. And in Fourier, it is alpha t by LC square. Okay. These LCs will be useful in calculating in Biot and in Fourier. So that's all for today.